Hello everybody and welcome to the module on hyperparameter optimization. I'm Lars Kotov, and in this video we will talk about perhaps the simplest approaches to hyperparameter optimization, namely grid search and random search. In grid search, we simply take all the hyperparameters that we have, the entire configuration space, and we discretize it along a grid, and then we try all the different values. This is obviously easy to implement and easily parallelizable. The evaluations are completely independent. I can do as many of them in parallel as I like, but unfortunately it scales exponentially in the number of hyperparameters, so we run into the curse of dimensionality here, and it also tends to search many irrelevant areas in practice. The discretization that this relies on into a grid can be somewhat arbitrary and is not entirely straightforward. If we have, in particular, if we have real parameters, real hyperparameters, where we have to decide on a granularity, because we can obviously not try every possible value. That would be simply too large, so we do have to discretize these in practice. On the right-hand side of the slide here, you can see an example of this. So here I have run a grid hyperparameter optimization on XGBoost. I have chosen two numeric hyperparameters, lambda and alpha here, and I have discretized these somewhat arbitrarily into the grid that you can see, and then I have evaluated each point on this grid here. And the result of this evaluation is the accuracy, or the mean accuracy over a cross-validation, where both the color and the size of the point shows you how well it has done. And we can see that the best performing configurations are in this corner here, so for low values of alpha and for high values of lambda, but obviously we have searched all of the other values here as well, so there are lots of values that essentially just tell us that, yeah, the performance is bad there, in particular in this region here, but we have still evaluated all of them. Another approach that is very common and that is perhaps a little bit better in practice is random search, where we uniformly sample from the configuration space. So this avoids the discretization that I've talked about before. We simply take samples uniformly at random from our entire configuration space and evaluate these. This is also easy to implement and also easily parallelizable, because I can take as many samples as I want, and then I can do all the evaluations in parallel and completely independently. I can also control how much to sample. In grid search, this is also possible to some extent through the discretization, but it's not as straightforward. So once I've decided on a discretization, that essentially tells me how many samples I have to evaluate, whereas I can always draw one more random sample. Or if I decide that I don't want 10 of them, I don't have to evaluate them. So I'm not bound to a particular structure here. Random search also tends to search irrelevant areas, but it usually gives us better coverage of the entire configuration space than grid search, in particular if some dimensions are unimportant, and in particular if we have discretized quite coarsely, which we might want to do to save resources for a grid search. In practice, it often performs better than grid search. And here on the right-hand side, we see the same example again. So I have taken the same configuration space. All I have changed here is the evaluation method. As you can see, the picture does look quite different. In particular, we have now discovered something good down here, where the values for both lambda and for alpha are relatively small. And this is something that the grid search did not discover, because it essentially fell in between two grid points. So here the discretization comes into play again, and we were not able to discover this with the particular discretization that we have chosen. You can also see that the coverage of the entire space is better. In particular, if you look at the log plots here and there for the x and y axis, you can see that many more different values were tried than for the grid search. Contrast that with the previous slide, where we have also different x and y values, obviously, but for one particular value for lambda, for example, we always try the same alpha value and vice versa, because that's how we discretize the grid. Whereas if we do this randomly, then we don't get the rows or columns exactly on the grid, and that's why we tend to have a better coverage in general here. So in summary, grid search Very simple, we simply try all possible values along a grid. We do have to think about the discretization here, but in many cases this is something that is not very difficult. Random search, we sample uniformly from the configuration space, so this usually covers the space better, and it is often a useful baseline to gauge the difficulty of a hyperparameter optimization task. If I run random search on this, so something that is very simple and not particularly sophisticated, how well does it do? Is it able to find something that improves over the default? How much are we improving? Just to get an idea of how difficult it will be to find an improvement on this particular data set.